Okay, in this problem, draw the shear force and bending moment diagram for the above beam. Here you can see throughout the beam, linearly distributed load is acting. You can see it's linearly varying. Its intensity is linearly varying. At this end, that is equal to 6 kilonewton per meter. And the beam length is equal to 9 meter. At this end, pin supported. At this end, roller supported. Let's mark these 2 points as A and the B. Okay, first of all, we need to find the support reactions. In order to find the support reaction, first we have to draw the free body diagram for the entire beam. Okay, let's start with drawing the free body diagram for the entire beam. At the roller support, let's take RB. There's no any lateral reactions, lateral forces acting on it, or any horizontal forces. So the imping support is lateral horizontal reaction is equal to 0. So only remaining is RA vertical reaction and linearly distributed load. This is the free body diagram for this beam. Okay, then this value is equal to 6 kilonewton per meter. At this end, the intensity is equal to 6 kilonewton per meter. So then the resultant, how to find the resultant of this distributed load? The resultant of this distributed load is given by the area of this triangular area. Other way you can find the its resultant by calculating this triangular area, or other way you can use the integral method to find the resultant force. The resultant force is equal. Resultant force R is equal 0 to 9 integral. At the x distance, what is the intensity? It is the x distance. What is the intensity? For 9 meters, intensity is linearly varying to 6. For x distance, that is equal to 6 divided by 9 into x. Okay, so that 2/3 into x, the intensity of the linearly distributed load at the x distance from the A, and let's take it is acting in a small dx length, so that the dx integral 0 to 9. So x we have to vary from 0 to 9. So then we can calculate the resultant force. The resultant is equal x square divided by 2 into 0 to 9 1/3. Then the R is equal here 81. Yeah, 81 divided by 6. 81 divided by 6. That's equal to 27 kilonewton. 27 kilonewton. Other way, similarly, you can find this resultant force by finding the area of this triangle. Okay. Then here there is 2 in here. Yeah. So 81. You can cut this one. 80. 81. Yeah. Then to find the where that is acting, the resultant force is equal to 27 kilonewton. So then where it is acting, so actually that is acting at the centroid. The resultant is acting to the centroid of this triangle. This is 27 kilonewton at the centroid, that is equal to here 9 meters, 3 meter distance from the B and 6 meter distance from the A point. It is acting, the reservoir force is acting. So other way you can find this by doing the calculation, you can find that one also. Let's take from here to here the resultant force kind of action distance. Let's take it as the x bar. So we are going to take the moment that means moment produced by the resultant force also should equal to the moment produced by the individual moment produced by the distributed load. So then that is where we are going to find the x bar into 27, there is a moment produced by the resultant force should equal to the moment produced by this distributed load. So how to calculate that one? For x distance, the forces acting is equal into dx, then into x into dx, the lever arm is equal to x integral 0 to 9, then we can calculate the total moment produced by this distributed load. So then x bar into 27 is equal, here 2/3 we can take it out, x into square dx 0 to 9 x bar into 27 into x into cube divided by 3 0 to 9. So then we can calculate the x bar easily. The x bar value is equal 6 meters. At the 6 meters distance from A, the resultant force is acting. Okay. Other way you can find by finding the centroid of this triangle section. Anyhow, from the basic method also you can find that one also. Okay, let's find the support reaction. Okay, let me draw the equivalent diagram representing the distributed load. Okay, the equivalent diagram I would represent this distributed load by the point load acting. The point load, that means the resultant of this distributed load is equal to 27 kilonewton. Then support reaction RB, here RA, this length is equal, we have found that one 6 meters, here it is 3 meters. So now we can easily find the RA and RB. RA we can write the equation for RB, 9 into 3 into 27, that is equal to 9 kilonewton. Then the RB is equal 9 into 6 into 27, that is equal to 18 kilonewton. Okay, now we are going to obtain the shear force equation and the bending moment equation. So to find the to obtain the shear force and bending moment equation, I'm going to introduce imaginary card. So I'm going to introduce imaginary card somewhere in here. The x distance from the A left hand side. So then I'm going to consider this separated beam segment separately. Okay. This is the segment. The RA value is equal 9. The shear force acting on this face, cutting plane, then the bending moment. Okay, bending moment acting on this cross section. If you take the adjacent plane that is acting other way around, this is via positive shear force acting upward direction on the adjacent plane, and also positive bending moment acting in other way around. Again, if we take the another cut somewhere in here that is acting again downward direction, then this is acting in this direction. So you can see acted shear force tends to rotate the beam segment in clockwise direction, and due to the act of bending moment, it is subject to a sagging bending, forming this kind of curvatures. Okay, this is how we are marking the positive shear force and positive bending moment. That is our sign convention. Okay, then let me mark the distributed load also. The distributed load, the length is equal to x. Distributed load is acting in this way. Okay. So what is the intensity of distributed load at this point? So it's a linearly distributed load. So for 9 distance, the intensity varies 6 to, for x distance, that should vary 6 divided by 9 into x is equal to 2/3 of x. Okay. Then the resultant, what is the resultant of this distributed load? What is the resultant of this distributed load? That is given by the area of this triangle. Area of this triangle is equal half, resultant half into base length and height of the triangle is equal to x. The r is equal x square divided by 3. X square divided by 3 kilonewton. Similarly, we can find the where it is acting by taking the centroid of this triangle. It is acting to somewhere in here. The distance 2/3 of x and 1 over x, like this. Okay. So then we can find again. I'm going to do the equivalent diagram representing forces acting on this beam segment. Let me do the equivalent diagram. Shear force and the bending moment acting, then the resultant of distributed load acting somewhere in this kind of position. That value is equal x square divided by 3. The distance from A is equal 2 divided by 3 into x, 1 divided by 3 into x from here. So then here another point, support reaction 9 kilonewton force is acting. So now we are ready to find the shear force and the bending moment equations. So by resolving all the forces in vertical direction, 9 minus x square divided by 3 minus shear force is equal to 0. Then by making the shear force into subject, the shear force is equal minus x square divided by 3 plus 9. Here you can see the quadratic equation passing through the coordinate center, the symmetric axis passing through the coordinate center, because x symmetric is equal minus b over 2a. The b is equal 0, so that symmetric axis is equal 0. The parabola having the maximum at x is equal 0, the maximum, the shear force maximum value is equal 9. By substituting the 0 in this equation, we can calculate that one. That value is equal 9. So then at x is equal 9, at x is equal 9, the shear force at x is equal 9, the value is equal, by substituting the 9 instead of x, by substituting the 9, we are able to find that value. That value is equal minus 18. Then you can see parabola having the maximum at 9 and at x is equal 9, that is equal to minus 18. So it is intersect x-axis. So where it is intersect the x-axis, how we can find? By equating the shear force equal to 0, we are able to find the value where the curve is intersecting the x-axis, minus x square divided by 3 plus 9. So then x is equal, by finding the square root of 27, is equal 5.2 meters. At the 5.2 meters, the shear force is equal to 0. That means it intersect x-axis at x is equal 5.2 meters. Okay. So then again, similarly, we can find the equation for the bending moment. Let's see how to find the bending moment equations. By taking the moment around this A point, then here the force is x square divided by 3. The lever arm is equal 2 divided by 3 into x. That is minus shear force into x plus bending moment is equal to 0. Okay. So then by making bending moment into subject, here 2x into cube divided by 9 plus x into shear force. The shear force, we have found the shear force value, minus x into square divided by 3 plus 9. Then the bending moment is equal 2 into x into cube divided by 9 plus, here it is negative, minus x into cube divided by 3 plus 9 into x. So then the finally bending moment is equal, by simplifying this 9 into 3 minus x into cube divided by 9 plus 9x. Okay, for the bending moment we are having x to the power of 3 equation. So to draw the graph, we need some more informations. Its maximum value and intersection points we have to find. Anyhow, you can see the bending moment at x is equal 0, the bending moment also equal to 0. Then the bending moment at x is equal 9, that value also equal to 0. So then let's find the maximum or minimum values. Let's take the derivation of this bending moment d to find the maximum or minimum values. Dx is equal minus 3x square divided by 9 plus 9. At maximum, this should equal to 0, maximum or minimum. At x is equal 81 divided by 3, the 27 is square root of 27, that is equal to around 5.2 meters. It having the curve having the maximum or minimum. So let's take the second derivative, d2 bending moment dx square, that is equal to second derivative is equal minus 2x divided by 3. Here you can see that is negative for any x value, so that at 5.2 meters curve having the maximum, so we can find the maximum value. Bending moment x is equal 5.2. we are going to find the maximum, having the maximum value by substituting the 5.2 in this equation. We can calculate the maximum value. That maximum value is equal 31.2 kilonewton meter. So now all the data we are having, so now we are ready to draw the shear force diagram and the bending moment diagram. Okay, let's see how to draw the diagram. Now we are ready to draw the shear force and bending moment diagram. These are the summary we obtain. The shear force equation, the equation at the maximum value of the shear force is equal to 9. Shear force at x is equal to 5.2, that is equal to 0. That means that shear force curve is intersecting x-axis at the 5.2. X is equal to 5.2. At shear force x is equal to 9 at this point, this shear force is equal to minus 18. Okay, so this is the bending moment equation. The bending moment x is equal to 0, the bending moment also equal to 0. Bending moment x is equal to 9, at the end the bending moment also equal to 0. So bending moment is maximized at the x is equal to 5.2, with the value we have found, the 31.2 kilonewton meter. Okay, let's now we can draw the bending shear force and bending moment diagram. Okay, first of all, let's start with this shear force diagram. The curve should passes this point at 9, that is equal to minus 18 kilonewton. At x is equal to 0, and maximum is the 9. This is the point and this is the point. So then we can draw the graph. Parabola passes through this point, and we have to do in this one also. Finally it goes to 0 at the roller support. On the roller support, that goes to 0. Okay, then similarly we can draw the bending moment diagram. Somewhere in here, 31.2 kilonewton meter, the maximum. So then the curve passes through these 3 points. You can draw the graph smoothly like this. This is the bending moment curve and the shear force curve. This is how we are solving this kind of linearly distributed load beam problem. Okay, thank you very much.